Okay, acid-base reactions. So we talked about precipitation reactions. Now we're going to talk about acid-base reactions and gas evolution reactions. And these are also types of reactions that can happen when we swap partners. And so we can use that same idea of these ions coming to a party, and we're going to swap partners and see if anybody, has any chemistry. In an acid-base reaction, we've got an acid and a base, hence the name. This is also often called a neutralization reaction because the acid and the base will neutralize each other. Generally, they produce water and some sort of a salt, an ionic compound. A gas evolution reaction, as the name suggests, a gas is evolved, a gas is formed. So here we mix these two things together and we see bubbling or fizzing. Anybody think of a reaction that you might have observed in the kitchen that does this? Baking soda. If you mix baking soda and vinegar, bubbles and fizzes. You put a little red food coloring in there, and you can pretend it's lava coming out of your little volcano that you made, right? It's a gas evolution reaction. Some gas evolution reactions are also acid-base reactions. So, as with a lot of things, some things fall into more than one category. So we've defined an acid before as a substance that produces hydrogen ions in aqueous solution. And this is known as the Arrhenius definition of the acid. Arrhenius was a scientist. I'm not going to get hung up on do you know the names of the definitions, but just be aware there are different ways of defining acids. So HCl. So HCl dissolved in water will ionize and form hydrogen ions and chloride ions. But what's really happening here is that this hydrogen ion leaves the hydrogen chloride molecule and goes and rides around on a water molecule. Because if we think about it, what is a hydrogen ion? A hydrogen atom has one proton and one electron. A hydrogen ion has one proton and no electrons. It's a bare proton. It's way smaller than the atom. It's too small to be out by itself. So I think of a hydrogen ion as being like a 3-month-old baby. Do you see them out on the street by themselves? They can't walk, right? They're not out there. So I think of the water molecule as sort of a babysitter. And so the water molecule can hold this hydrogen ion and take it out for a walk, right? So we don't actually see hydrogen ions alone in a solution. What's actually happening here is that the hydrogen ion from that is attaching to a water molecule to get this hydronium ion, H3O+. Now, we often use H+ and H3O+ interchangeably because just talking about the H+ makes all of the chemical equations much simpler to write. What we do is we just understand, just like we do with a 3-month-old baby. If I'm talking about, this baby was at this place, we kind of assume that an adult brought it there, right? We don't need to tell each other that. Somebody, a parent, a babysitter, somebody brought the baby there. So when we see hydrogen ion aqueous, we know that hydrogen ion isn't floating around by itself. It's actually riding on a water molecule. Everybody okay with that? So it's losing a proton. A hydrogen ion is a proton. And so we have what are called polyprotic acids. So poly meaning many, many protons. They have more than one ionizable hydrogen, ionizable proton. And they will release these one at a time. So an example is sulfuric acid. Sulfuric acid is H2SO4. It has 2 hydrogen ions that can ionize, and those are the ones in the front. So it's called a diprotic acid. if we look at what happens when we put H2SO4 into water, the first thing that happens is we get one hydrogen and the hydrogen sulfate ion. And then the hydrogen sulfate ion also loses a hydrogen ion and becomes a sulfate ion. So they lose them one at a time. Yeah, there are two separate reactions. And some of this is stuff that we don't really get to until Chem 1B. But with H2SO4, this first reaction where we lose one proton, that's a strong acid. It loses all of the molecules lose one of their protons. And then this thing that's left, this hydrogen sulfate, is actually an acid because it can lose another hydrogen ion. But this is a weak acid, and it only does this a little bit. Another polyprotic acid is phosphoric acid. We call that a triprotic acid. Because it has 3 protons. If we look at something like, I don't have enough room here, HC2H3O2. So that's an acid, right? One of the hydrogens is out front, and 3 of them are in the middle here. That's because only one of them is ionizable. That's the hydrogen ion, and what's left here, C2H3O2 minus, is acetate ion. Acetate ion doesn't lose any of its hydrogens. So that's why we only write one of the H's in front. It's always the ones in front that can be coming off as ionizable protons. Any questions? So the Arrhenius definition of a base is a substance that produces hydroxide ions in aqueous solution. So things like sodium hydroxide. So sodium hydroxide, soluble ionic compound, separates into sodium and hydroxide ions. There's the hydroxide ions. This is a base. There are other bases that are a little more difficult to recognize. When we look at sodium hydroxide, we see OH. We see the hydroxide. And in the name, sodium hydroxide. And anytime you hear hydroxide, you should think, oh, that's probably a base. But then we have some other bases like ammonia. Ammonia also acts as a base, but it doesn't have any hydroxide ions in it. And so it acts as a base, produces hydroxide ions by pulling hydrogen ions off of water. We'll talk more about that later. Some bases can produce 2 moles of hydroxide per mole of base, so like strontium hydroxide. When 1 mole of this dissolves, we form 1 mole of strontium and 2 moles of hydroxide. So if it was an acid, it'd be a diprotic acid. We don't have a name for bases like that. It's just, you just look at the chemical formula, and this tells me I'm going to get 2 moles of hydroxide. So in the neutralization reaction, we've got the acid that makes hydrogen ions, and we've got the base that makes hydroxide ions, and those come together to form a water molecule. So we've got the cation from, we've got the hydrogen and the hydroxide making water. And then we've got the cation from the base, the sodium, and the chloride from the acid, the anion, and those come together to make a salt, an ionic compound. So if we write the complete ionic equation and then cross out the spectators, we end up with a net ionic equation that looks like this. Hydrogen ions plus hydroxide ions make a water molecule. Any questions? This is the net ionic equation for most neutralization reactions. So let's look at that in picture form. So here we've got hydrochloric acid, and in the hydrochloric acid we have chloride ions and we have hydronium ions. The hydrogen ions from the HCl are sitting on a water molecule because they're too small to be hanging around alone. And then over here we've got the sodium hydroxide solution, which has sodium ions and hydroxide ions. When these mix together, the hydronium ions, which is water with an extra hydrogen, and the hydroxide ions, which are water that's missing a hydrogen, they get together, and the hydronium says, this hydrogen's getting heavy. Hey, you've only got one here, you carry him. And so they pass them off, and they go back to being just water. And that leaves the sodium ions and the chloride ions just hanging out. Some questions? Is water a stable compound? Yeah, it's really stable. So if things can make water, they typically do. Okay, so here we've got the acids. So these are the 6 strong acids. And yeah, you gotta remember it's these. So how do you do that? Well, we've got Cl, Br, and I, right? The halogens. So HCl, HBr, HI. Who's above Cl in that list? Fluorine. I think of those as the halogen sisters, right? They're nonmetals and they're in the same family, so they're sisters, right? And the little ones at the top, and they get bigger as they go down. So fluorine is the youngest sister, and she's too young to be strong. Okay, she's weak acid, HF. So down here we have hydrofluoric acid, but that's a weak acid. Her bigger sisters are strong. These are strong acids. And then nitric, sulfuric, and perchloric acid. I got nothing. So those 6 are strong. Any other acid is weak. Okay, so you just have to remember 6 things. For the bases, metal and hydroxide. Any metal hydroxide, I would expect you to tell me that's a strong base. And the only weak base that you are responsible for is ammonia. So ammonia is a weak base. Ammonia doesn't look like a base. NH3 doesn't look like a base. But down here in the fine print, this is what it does. NH3 reacts with water, and it will pull a hydrogen ion off of the water, and so it produces hydroxide ions that way. So it's a base even though it has no hydroxide in it. It's a weak base though. It doesn't do it very much, it just does it a little bit. Okay, so write a molecular and a net ionic equation for the reaction that occurs between aqueous HBr and aqueous LiOH. So they gave us the formulas for the reactants, and they told us what their states were. HBr, aqueous, LiOH, aqueous. And this is going to react. We still need to look at the formulas for the ions with their charges. So HBr, when it dissolves in water, forms hydrogen ions and bromide ions. Lithium hydroxide forms lithium ions and hydroxide ions. So to predict the products, we're going to swap partners and see what happens. So we'll put the H plus with the OH minus. And we'll put the lithium with the bromide. So if I'm not thinking, just kind of going by patterns, and I see H plus and OH minus, oh, well, their charges are opposite. I just need one of each of them. It's HOH. It's like, huh? Right? It's like, read it, huh? What is that? That's water, right? That's H2O. What's the state of water? It's a liquid. Can water be aqueous? It's a little silly, right? Water dissolved in water? No, water cannot be aqueous. So there's H2O. And lithium and bromide, I just need one of each. And then is that soluble or insoluble? Soluble. Lithium compounds are always soluble. And then I would need to balance this. Here I've got hydrogens in several places. Let's start something else. Br, one Br and one Br. One Li and one Li, and let's hope the others are fine. Got oxygen and oxygen, two hydrogens, 1 plus 2, two hydrogens. So there's my molecular equation. Now, it doesn't ask me to write the complete ionic equation. You, of course, can do that, but we kind of already have that down here. HBr is a strong acid, so that should be written as ions. This is an ionic compound, should be written as ions. How about water? Should we separate that into ions? No, because it has the state symbol L. So that one we just need to be H2O. And this is aqueous, so lithium and bromide. So now we can see who is the same on both sides. There's two spectators. Did bromide get into a relationship? Form a solid or a liquid or anything? No. There's bromide and bromide. We can cancel those out. Lithium and lithium stayed the same. So what I did there is I'm looking at this like this. These guys are all ions. I rewrote this one because it does not get separated, and so this is what I'm seeing in my mind. And then I see that the lithiums don't change and the bromides don't change. So then my net ionic equation is H plus aqueous plus hydroxide aqueous to form H2O liquid. Any questions? Let's do another one. Write the net ionic equation for the reaction between aqueous HCHO2, a weak acid, and aqueous NaOH. Before I can write the net ionic equation, I need to write a molecular equation. So I have HCHO2, aqueous. Now, they didn't really need to tell us that's a weak acid. This is an acid because it starts with H. It's not HCl, HBr, HI, H2SO4, HNO3, HClO4, the 6 strong acids. It's something else. We didn't learn how to name it, but that's okay. We can do reactions with it even though we don't know its name. And aqueous sodium hydroxide. I need to figure out what the products are. And I do that by separating them into ions and switching partners. So this is a strange acid. We haven't looked at that one before. You take the hydrogen off, and you write everything else as the other ion. So this is H plus and CHO2, and what would its charge be? -1, right? It had one hydrogen. I remove that H plus. What's left has to be CHO2 with a -1 charge. And then here, sodium and hydroxide are sodium ion and hydroxide. I'm going to predict the products by swapping partners. So I get H plus with OH minus, and I get sodium with weirdo that I wrote wrong. There we go. If you get the formula, if you change the formula, it becomes really difficult to balance the equation. So when I put H plus and OH minus together, how do I write that? H2O. And water is a liquid at room temperature. If a temperature isn't specified or implied, assume room temperature. And then here, I'm going to have NaCHO2, putting those two together. Aqueous or solid? Aqueous. Because sodium compounds are always soluble, no exceptions. So there's my predicted products. We should check to see, is this balanced? Sodium and sodium. There's a CHO2 and a CHO2. And then I've got this hydrogen with that hydroxide making this one right here, so that one's balanced. I can use my little notes down here as my informal complete ionic equation. This one's a liquid, so I need to keep it together. But all of the rest of them so is that okay? No, it's not quite okay. This is a weak acid. Weak acids are present mostly as the intact molecule. They only ionize a little bit. So this is one of the rare aqueous things that I do not want to separate because it's a weak acid. That one's a bit tricky. There will probably be one example, one question on the next exam that'll try to trick you with a weak acid like that. But you could actually be quite successful in Chem 1A without remembering to not separate your weak acids when you write net ionic equations. That's not a huge deal. So what are my spectators then? Just sodium. Nobody else. So for my net ionic equation, I'm going to copy down what's left. I've got my weak acid. It's not EQ, it's AQ. And I've got hydroxide ion. And that's making water, liquid, and CHO2 aqueous. So that's my net ionic equation. Does that mean that this is all that's present in that beaker? Does this mean that the sodium ions disappeared? No, the sodium ions are there. I cannot have hydroxide ions, these are negative, without some positive ion. You can't have a beaker of just cations. It doesn't work that way. So it looks like the hydroxide ion is alone here, but it's not. There's a spectator ion. Nobody comes to this alone. This one's coming in with a partner, and this guy's leaving with a partner, but sodium didn't get involved, and so we don't show it in the Ionic equation. Any questions?
For the HCH2, is that for like every weak base and weak acid that doesn't?
Yes, any weak acid, you don't separate it into ions. You pull it apart to see how it's going to react, because what happens is it does this a little bit, and so it does that a little bit, and these hydrogen ions react with the hydroxide. And so then a little bit more does that. And so it can eventually react completely. But we want to describe what does the solution look like. And so it looks like mostly these molecules in solution. A weak base, the only one we're going to run into is ammonia. And that's not so tempting to separate, because how do you separate NH3? Anybody else?
So our net ionic equation is essentially just the reactant.
The net ionic equation describes the things that actually reacted, that actually changed. There could be lots and lots of other stuff that just the same before and after. So that it's like your net paycheck, right? That's the money you actually get to do something with. The withholding taxes and the Social Security and all of that stuff, you don't get to use that. It's probably better just not even to look at that part, right? Just look at the net paycheck. And then you won't get so depressed about how much money the government is stealing from you. So acid-base titrations. A titration is a technique. And in an acid-base titration, we're using an acid-base reaction or a neutralization reaction. The point of a titration is to use a solution whose concentration we know to find the concentration of an unknown solution. So we add the one solution to the other until the reactants are in their stoichiometric ratio. We call this the equivalence point. And then we calculate the unknown concentration using stoichiometry. So you might wonder, well, how do I know when I've added enough? So I've got an acid and a base, and maybe I'm adding base to the acid. How do I know when I've added just enough to react with all of the acid? Well, the simplest way is to use an indicator. Indicators are compounds, typically organic compounds, that change color in different pHs. So at the equivalence point, if I'm adding base to an acid, the acid was acidic, I'm adding base. At the equivalence point, it's neutral because I've added just enough hydroxide to neutralize all the H+. And then I add a teeny tiny bit more, and now the solution becomes basic, and the color changes. And that tells me to stop. Pictures and illustrations. And we're just looking at the net ionic equation here because it really doesn't matter what the other ions are. So we've got hydrogen ions and hydroxide ions forming water molecules. In the flask, we've got the hydrogen ions. This might be HCl, strong acid, so we've got lots of hydrogen ions. The chlorides are just going to be spectators, so we're ignoring them. Here in the burette, we have hydroxide ions. We use a burette for this because we can add sodium hydroxide a drop at a time if we need to, and we can use the graduations on the burette to measure how much we've added. So we have an indicator in this solution. This indicator is phenolphthalein. It's colorless in an acidic solution. As I add sodium hydroxide, the hydroxide ions are going to react with the hydrogen ions and form water molecules. And I'm going to keep adding them until I have reacted all of the hydrogen ions. That causes the pH of the solution to change. And typically we go a teeny tiny bit over. It's unavoidable. And the solution turns pink, and we know we've added enough. So at this point, we can measure the volume of sodium hydroxide that we added, and if we know the concentration, the molarity, we can calculate how many moles of hydroxide were added. If we know the initial volume of this solution, and we know how many moles of hydroxide, then we know the moles of hydrogen ion, and we can calculate the concentration. Here it is in pictures. So it looks like we're adding water to water, and after a while, we'll start to see some localized pink color here, but then when you mix this, it interacts with more hydrogen ions, and it goes away. And when you're finished, it'll all be pink. Now that person overshot the endpoint. You don't want it to be that pink, but you get the idea. We will be doing several titrations in this class. Yeah. We'll do this in lab. Yep, at least 3 times, maybe more. And we're going to do it old school with glass pipettes. There are, of course, a number of different ways that you can use instrumentation to do the titration now, but that's way too complicated for a teaching lab, so we just use the glass burettes. It's a good time. So we'll do it in lab, but we also need to know how to just do calculations if we're given the information. And this comes down to solution stoichiometry, which we've already learned. It's just that it happens to be with an acid and a base, and now this question isn't giving us the balanced chemical reaction. They're going to make us figure it out. So the titration of a 20 ml sample of an H2SO4 solution of unknown concentration requires 22.87 milliliters of a 0.158 molar KOH solution to reach the equivalence point. What is the concentration of the unknown H2SO4 solution? I need a balanced chemical equation. So that's what we are learning how to do today. So I've got H2SO4. In these problems, we generally don't need to think about is it aqueous or not. So we often just leave the state symbols out. We've got H2SO4 and we've got KOH. And those are going to react and form something. How do we predict the products? Swap partners. Okay? So KOH is potassium and hydroxide. This H2SO4, that's a diprotic acid. I told you earlier it's strong in the first hydrogen, it's weak in the second. We don't need to worry about whether it's weak or strong. In a titration, all of the hydrogen ions react. So this is going to be H+, and we're going to look at that ion, the sulfate, with all of the hydroxides off of it. All of the hydrogen ions off of it. So we're going to swap partners. And we're going to get H+ with OH-, and potassium with SO4 2-. So the first one is H2O. And what's the formula for the second one? K2SO4. Because I need 2 of these potassium ions to balance the charge on that sulfate ion. I do not have to do a complete ionic equation or a net ionic equation. I just need the molecular equation. It does need to be balanced, though. Is this balanced? No. The time when you're really going to have to worry about balancing it is when you have a diprotic or a triprotic acid or you've got something funky like calcium hydroxide with 2 hydroxides. So with something like this, the sulfates are staying together. I've got 1 sulfate here and 1 sulfate there. This potassium, I've got 2 potassiums here and only 1 over there. So I'll need to put a 2 in front of the KOH. And then let's check the hydrogens out. I've got 2 hydrogens here, and I've got 2 here, and only 2 there. So I need 2 plus 2, I need 4. So if I put a 2 there, and then that also takes care of the rest of the oxygens. So I don't really need this part anymore, so I'm going to get rid of that. Now that I have my balanced chemical equation, I'm going to take those numbers and write them underneath. So it says I have 20 milliliters of H2SO4. So 20 milliliters of that. And it says I have 22.87 milliliters of KOH, and that the concentration is 0.158, capital M, moles per liter. And then what am I trying to find? What is the concentration of the H2SO4? It doesn't specify what unit for concentration. It's going to be moles per liter. Yes? That's a good question. Is this technically a dilution? Well, there is dilution occurring because I'm combining 2 solutions, and so the concentration of the sulfuric acid in the mixture would be less, but what we're interested in is the concentration in the original solution. And we cannot use the dilution equation, M1V1, because we have a chemical reaction occurring. Yeah. And again, if a tutor says, oh, you can use M1V1, say no. Could I have a different tutor, please? Mrs. K said I couldn't do that. Please send them over to me or get their name and report them, because that's just really, really wrong. This is stoichiometry. So what's the chant for stoichiometry? Grams to moles to moles to grams. I can change up the ends. The middle, it's always moles to moles in the middle. Always, 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 always moles to moles in the middle. Sometimes you can cut it down just to the moles in the middle without anything on the end, like some of those worksheet problems where it was asking you, it gives you moles of this and asks for moles of product. And then people got confused and thought, well, am I supposed to go to grams in the middle? Nope, just moles to moles. We were trying to make it easy for you and ended up making it more difficult. So moles to moles in the middle, but what am I starting with? I'm not starting with grams. I've got milliliters. And what am I ending up with? Well, I want moles per liter. So what I really need is moles, and then divide by the liters, right? Moles, molarity is moles divided by liters. So if I stop at moles here and then divide by the volume in liters, I'll have my molarity. Any questions? So we've got liters and milliliters. So I'm going to introduce you to my friend millimole. So I'm going to rewrite this a little bit. So I have that concentration, moles per liter That means there's 0.158 moles of that in 1 liter. Is that going to be changed if I put milli in the top and milli in the bottom? No. Because the millis cancel out. It's still the same number, right? It's like if I take 2/3 and multiply it by 2/2, that gives me 4/6. 4/6 is the same as 2/3. It just looks different, right? So that's what I'm doing here. Because almost all of these problems are going to be milliliters. So if I use millimoles, then I don't have to deal with the liters, and we'll see something fun happen at the end so that we can get molarity back. Okay, so I've got a volume of this and a concentration. So I'm starting with KOH, 22.87 milliliters of KOH. And I'm going to convert that. I'm going to do milli everything. I'm going to go to millimoles of KOH, and I'm going to have milliliters in the denominator. And then I'm going to go to millimoles of H2SO4, and I'm going to have millimoles in the denominator of KOH. So I'm making this millimoles and millimoles. So the molarity here is the same number. I just made the top and the bottom milli. And so this is 0.158 millimoles per milliliter. And then my mole ratio is 1 mole of sulfuric acid to 2 moles of KOH, which is the same as 1 millimole of H2SO4 to 2 millimoles of KOH. So in front of the H2SO4 is a 1, and in front of the KOH is a 2. (22.87 times 0.158 divided by 2). And so my calculator is giving me, and that would be millimoles of H2SO4. How many significant figures should that have? 3. The volume has 4, but the concentration only has 3. So if I want molarity, concentration, that's moles over liters. So if I take 1.80673 millimoles and divide by the volume, 20.00, no, it's just 0, 20.0 milliliters. I can cancel the millis out, and I'm left with moles per liter. And I didn't actually have to convert between liters and milliliters at all. So 1.80673 divided by 20. Should have 3 sig figs, 0.090336. 0.0903 moles per liter. Any questions? Bless you. 0.0903 mole.